Okay. Hello everyone, and welcome to the Physics Northwest mock paper one of 2022. So I'm sure you have the questions for Physics Northwest mock paper one. So we'll just go through the questions. So question one is about question one reads, which of the following is correct? A non-homogeneous equation may be physically correct. We have A, B, C, D. So A says a non-homogeneous equation may be physically correct. No, a non-homogeneous equation may not be physically correct. So if an equation is non-homogeneous, for example, this is a non-homogeneous equation, right? There is no way a non-homogeneous equation may be physically correct. Okay, a non-homogeneous equation must be incorrect, must be physically incorrect. B says a homogeneous equation must be physically incorrect. A homogeneous equation must not be physically incorrect. It may be physically incorrect. So a homogeneous equation, for example, this is a homogeneous equation. This equation is homogeneous. The kinetic energy of a body, for example. This equation is incorrect. So it must be incorrect. It must not be incorrect. It must not be incorrect. So a homogeneous equation may be physically incorrect. This is it. But it must not be. So the reason why it must not be incorrect because this is a homogeneous equation that is correct. Okay. Question C says a non-homogeneous equation must be physically incorrect. So a non-homogeneous equation must be physically incorrect. That's true. For example, this is a non-homogeneous equation, the force. So this equation must be physically incorrect. And a homogeneous equation must be physically, and D says a homogeneous equation must be physically correct. So D is wrong. So the right answer for question one is C. So you can follow through with the questions, or you can download the PDF of the questions so that you can follow through the answers using the question sheet. Okay. We'll go to the next question. Question two. Question two talks about if a stone is tied to a string and is wheeled to move in a vertical circle at a speed v, then the string is most likely to break. At what point is the string likely to break? At what point is the tension is maximum? The sense of the acceleration. If the string breaks, the stone will continue to move in. So which of these is correct? So you want to simulate a stone that is being wheeled around in a vertical circle. So if we consider let's consider a vertical circle. Yeah. Okay. Let's consider a vertical circle. Let's consider this is the center of the circle and this is the stone. We have 3 points. Let's call it A, B, and C. Let's call this point here D. Okay, so we have the stone. The stone can be at any point here. So at point A, we have the weight. So the weight of the stone acts downwards, and the tension in the string is pulling the stone towards the center. So you have the tension in the string plus the weight of the stone is equal to the mass times the circular acceleration. So the tension is equal to times mg. That's at A. This is the tension in the string. At B, what we have is we have the weight acts vertically downwards, and you have the tension acts perpendicular to the weight. So we have the tension minus mg. There's no horizontal component of the weight, so it's 0 equal to m omega squared r. So that's just the tension. At C, so at C here we have the tension, and we have the weight acts downwards. So the tension minus the weight is equal to m omega squared times r. So the tension is equal to m omega squared r plus mg. Okay, so we have this at C, and at D, we have the weight acts downwards, and let's say it acts as an angle theta. So this is mg sine theta, mg cos theta self. This times mg cos theta equal to m r squared. So if we look at, if the string is most likely to bring vertically below the center. So if you look at point C, the tension is this term plus the weight plus this term, which is the maximum. At B, it's just m omega squared r. At A is m omega squared r minus mg, and this is less. So the tension in the string is maximum at C. So A is the correct answer. The tension in the string is maximum when the stone is vertically above. Of course, B is wrong. The sense of the acceleration changes with direction of the velocity. The sense of the acceleration doesn't change. If the string breaks, the stone will continue to move in a circular path. Of course not. If the string breaks, the stone would move in a tangential direction to the circle. because there's no centripetal force holding the stone. Okay, we move to question 3. So question 3 talks about the amount of energy needed to convert pure water at 60 degrees to steam. So to convert pure water at 60 degrees to steam, you need to increase the temperature of the water. And then you need to increase the temperature of the water. So this happens by increasing the temperature to 100 degrees and then converting it to steam by using the latent heat of vaporization. So we have the latent heat of vaporization, the specific heat capacity of water, So if you feed everything here, you have the mass of water, 1.2 kg, times the specific heat capacity of water, times the change in temperature to raise water from 60 degrees to 100 degrees, times again the mass of water, times the specific heat, latent heat of vaporization of water. And this gives you 2913600 joules, which is C. So question 3, the answer is C. So we move to question 4. Question 4 is talking about damping, different kinds of damping. So for question 4, for a moving coil metal to function properly, you can have a metal like a volt metal or some coil metal where you want the pointer needs to make a swing and then rapidly returns to equilibrium. You need to damp it. What kind of damping would you give a coil? So if you look at the graph for damping, we have something like this. Let's say we have something like this. Let's say we have the horizontal line here. You have different kinds of damping, okay? Let's say we have an object that oscillates, continues to oscillate, and really doesn't go to equilibrium that fast. This right here we're going to call this right here is called underdamped. This is underdamped because it doesn't go to equilibrium that fast. Okay. So we have another one here. Let's call it we're going to call it critically damped. The reason is that this one starts at the high amplitude and quickly goes to equilibrium. So we're going to call this critically damped. We have a third one. We're going to call this one starts at a high amplitude and just